So we've been talking about infinite series for the last few lectures, and this is what an infinite series looks like. You're adding up a bunch of terms. This a sub n could represent 1 over 2 to the n. It could be, and then you'd have a geometric series. It could be 1 over n cubed, and then you'd have a p series. So there's a lot of different elements you could put in for a sub n, which would give you a different series. But in general, what did these series do? They converge to some number, or they diverged. So what we're going to do today, and this is what we've been kind of building up towards, we're just going to take this same series, and the only thing different, and I've been saying all along, it doesn't matter where we start, we're going to start at 0. And instead of calling it a sub n, there's nothing wrong with calling it a sub n, but I'll show you why. I'm going to call it c sub n, but it represents the same thing. And then, what's really new, we're going to add x minus a to the n. And that's why I'm calling this c sub n and not a sub n, so you just don't get mixed up with that a. So x is a variable, a is a constant. So what is it going to look like when you write it out? When n is 0, you get c sub 0 times something to the 0 power, so that's just 1, plus c1 times x minus a to the first, plus c2 times x minus a squared, and it keeps going. It's an infinite series. But it's not a series of just numbers that you're adding up now. Now we have variable x in here. So we have x to the 0 power, a constant, plus something times x to the first power, plus something times x to the second power. What we have is an infinite polynomial. And it's got a special name. It's called a power series. And that's going to be something that we're going to be dealing with for a while. And they're going to be pretty important. So all a power series is, you first look at it and say, oh, that's really complicated, but it's really just a polynomial. Like 1 plus x squared minus 3x cubed. It's just got a bunch of x terms in it. But the unusual part of it is it goes to infinity. So let me just give you an example of one. Let's pick the simplest one we could think of. So what I'm going to do for my a sub n, in this case I'm calling it c sub n, instead of having something complicated like this, I'm going to just make all the a sub n's just be 1. So it'd be like adding up 1 forever. So c sub n is just 1, and I'm going to call a 0, this constant. So then what do you get? It's just x to the n. So if you wrote it out, it would be x to the 0 plus x to the first plus x squared, and it keeps going forever. So there's the first power series you've actually seen. And it happens to be kind of a special power series because you've seen something like this before, where you're adding up terms, and to get to the next term, you multiply by the same thing every time. X times 1 is x times x is x squared. So this is a geometric power series. And we even know what it adds up to. It adds up to the first term over 1 minus r. And in this case, r is x. And this should look kind of amazing. What do we have? We have a function that's not a polynomial, that's equal exactly to this polynomial. I think that's pretty exciting. Now, there is one caveat to this. We know geometric series only converge when r is less than 1. So this is a true statement, but it only is true when the absolute value of x is less than 1, so between -1 and 1. But if I pick any number in this interval, like 0.3 or 0.7 or 0.8, if I put it in here, I'm going to get the exact same thing here as I put in here. Now, the downside of that is that I have to add up an infinite number of things. So you're never going to really have a chance to add up an infinite number of things. You're always going to have to approximate. Say I wanted to approximate this function with this polynomial, I'm going to have to stop at a certain point. And I can only use numbers in this case between -1 and 1. That's also a little bit of a downside. Now, think about this for a minute. If you're picking a number that is between -1 and 1, is the accuracy, if you stop at a certain place, like say we stop right here, is it going to be more accurate for 0.7 than it is for 0.3, or the other way around, or doesn't it matter? Well, think about if you stopped right here, what would be the error? What would be what you left off? X cubed plus x to the 4th all the way on. So you can see the bigger x is, the more the error is going to be. So it should do better at 0.3 than it does at 0.7. And where is it going to do perfectly? At 0. And you can see that right here. If you put in 0, what do you get? 1 plus a bunch of zeros. Over here you get 1. So it works perfectly at 0, and the farther away you get, the worse it should be. So what I did over here is I took the original function, 1 over 1 minus x, and graphed it in black. And it goes like this and like this. It's got an asymptote at x equals 1. But we should only really be looking at comparing this function to these polynomials between -1 and 1. You can see it's going to do terrible down here because I've graphed the polynomials up there. But it does a pretty good job between -1 and 1. So what would be the absolute worst polynomial of these? It would be if you just used 1, y equals 1. Then you'd be approximating this black curve between -1 and 1 with just this horizontal line. Well, you can see it does perfectly at x equals 0, but then it gets quite a ways away from 1 over 1 minus x. Well, let's up it a little bit. What if you use y equals 1 plus x to approximate this function? Now we've got this straight line right here. And you can see that that does a pretty good job of approximating this curve between -1 and 1. Well, what if you take one more term? Now you've got 1 plus x squared. We've got a polynomial. I mean a parabola. So that's this red. And you can see because of the curve, it does better than this straight line. It starts to get closer and closer to 1 over 1 minus x. And the more terms you add, so if I add an x cubed, then I get a cubic. And you can see this cubic can do a better job of hugging up against this black curve. So the more terms I take, the better it goes. Now, besides the graph, I plugged some values into the calculator to show you. So at 0.7, that's getting farther away from the center here, 0. So it's not going to do a great job here. So what happens when you plug 0.7 into 1 over 1 minus x? You get 3.3. Well, if you use this horizontal line, I didn't write it down, but that's always going to say 1. Well, 1 isn't very close. If I plug it into this blue line, y equals 1 plus x, I get 1.7. Still, not too close. If I plug it into the parabola, I get 2.19. I'm getting closer. And if I plug it into the cubic, I'm getting closer yet. So that kind of confirms what the graph is saying and what makes sense. But what should do better is if I plug 0.3. So I did the same thing with 0.3, and I got 1.43. The horizontal line would just predict 1. Not as bad. The straight line on a slant predicts 1.3, getting better. The parabola this time predicts 1.39. But the cubic gives you 1.42. So you can see how well these polynomials can predict this function as long as it's within where it converges. Because once it doesn't converge, you don't want a series that's going to go to infinity to be approximating a function. And the closer you get to the center. And the more terms you use, the better. So, now you know a little bit about power series. So let's make one that's a little more complicated. Let's do the same thing. But now, instead of making c sub n 1, we're going to make it negative 1 to the n over 2 to the n. And instead of making a 0, we'll make a 2. So this is your second power series. So you see, these are just, that would be like the series we've looked at before, and we're just adding this polynomial part. So if you put in some values of n, you still get a 1 here, because to the 0 power everything is 1. Then, when n is 1, negative 1 to the 1 is minus 1 over 2 times x minus 2 to the first. Then when n is 2, you get plus 1 over 4 times x minus 2 squared. And then it keeps going. Now, amazingly, this is one that also is a geometric series. It's just a little more complicated than this one, because to get from this term to this term, and from this term to this term, you're always multiplying by negative 1/2 times x minus 2. So I can also find out what this series would converge to. 1 over, and r is 1 minus the r term. And the r term is negative 1/2 times x minus 2. If you just simplify this, you get 1 plus x over 2 minus 1. So you just get 1 over x over 2, or 2 over x. So now, instead of this function, I've got another function that we can represent by a different polynomial. And everything should be the same. It should do the best at x equals 2, because look at x equals 2, it's going to be exact. 2 over 2 equals 1, and every other term would go to 0. So the farther away you get from 2, the worse it's going to be. Now, we could find out where this converges by saying it's going to converge wherever, the similar part we did up here, we just say where r is less than 1 in absolute value. So the absolute value of that is just going to make this positive, and you're going to have, if you multiply by 2, you get x minus 2 is less than 2, and that's going to be satisfied by, it has to be between 2 and negative 2, or x has to be between 4 and 0. So this one does a little bit better. Instead of just going from negative 1 to 1, this series converges between 0 and 4. So I can use any value of x in there in this interval, and where should it do the best? At 2. The farther away you get from 2, the worse it's going to be. So I'm not going to graph this one. If you wanted to, you could graph these on your graphing calculator, and you should see something similar, that the more terms you use, the better they match. Instead, I just picked one value of x. X equals 3, which is in this interval. And this is what the function 2 over x looks like. 0.6 repeating. And then I just took one term, 1. Of course, you're just going to get 1. Then I used 2 terms. So if I use 2 terms, that's going to be a straight line. And that gave me 0.5. When I went to a parabola with 3 terms, I got 0.75. And then I went to 11 terms. There's something on your calculator that will add up as many terms as you want of a series. I didn't do all these by hand, and I got 0.6669 versus 0.6666. So you can see, as you start to take a lot of terms, this function is really well approximated by this polynomial. The difference is, out of the millions of functions that we have, we only have 2 functions, this one and this one, that we can represent by polynomials. And you're going to find out the more we can do, the better. So I thought I would just give you one more that doesn't turn out to be a geometric series. So one more power series. This is your third one. So n equals 0 to infinity. But this time, for c sub n, I'm going to put 1 over n factorial. And then for a, I'm going to put 0. So I just get x minus 0 to the n. So what does that series look like? You get 1, and then when n is 1, you get x. When n is 2, you get x squared over 2 factorial, but that's just 2. And then you get x cubed over 3 factorial, and that just keeps going. So this time I can't actually tell you what this infinite polynomial, what this power series converges to, if anything. But I decided, let's just plug some numbers into here and see what you get. So, I tried 2 values of x. I tried 1 and 2. So when I only took the first term of the series, of course, you're going to predict 1. When I did into 1 plus x, when I used 2 terms, I got 2. When I used 3 terms, I got 2.5. 4 terms, I got 2.6 repeating. And when I did 11 terms, when I plugged 1 in for x, I got 2.71828, which sounded kind of familiar to me. Anyway, I went and then plugged in 2. Of course, 1 is just going to predict 1. 1 plus x predicted 3. This gave me 5, 6.3 repeating, and then when I used 11 terms, I got this number. So we don't know what the function is, but we do know what? When you plug in 1, this might be pretty close. And when you plug in 2, this might be pretty close. And just for kicks, I started to remember what this number looked like. So I plugged in e to my calculator, and that's what I got, 2.718281828. And then when I plugged in e squared, I got 7.389, so close to this. Could this possibly be e to the x? I think it must be a coincidence. But wouldn't that be the coolest thing ever if we just randomly picked this power series and it turned out to be the function e to the x? Oh well, I'll have to think about that one. So anyway, these power series are really important, but the importance is only good where they converge. So this one was really neat, but it only worked for -1 to 1. The second one did better. This one we don't even really know because it's not a geometric series. And we do really want to know. So anyway, there is a way of finding out where they converge when they just don't happen to be geometric series. So there's a test. So the first thing you do, remember this is just a series. We've got a bunch of tests. So we're going to use the ratio test. Because it's pretty hard to find something to compare these two. So we're going to use the ratio test. You could use the nth root test, but very rarely. It's usually the ratio test. The trouble is, you can only use ratio tests on all positive terms. And now we've got these series that have x's in them, where x's can represent a lot of different numbers. So they could have negative numbers in there. So what we're going to do is use the ratio test, but to see if the series, the power series, converges absolutely. In other words, we're going to make all the terms positive so that we can use the ratio test, and then we can see where it converges absolutely. And what you're going to find out, and you'll see this in a couple of examples, the answer is often an open interval on the x-axis. So from 0 to 2, or from 1 to 8, not including the endpoints. It's an open interval. Often, it gets that. Sometimes, it's all real numbers. That's going to be a really good case if that happens, because then, if you did have this power series representing a function, you could do it for any value of x, not just the band of numbers that I showed before. And in some rare cases, and I wouldn't even worry about this, it converges only at a. And then the power series would be pretty useless. But that happens really rarely. Usually it's either an open interval or all real numbers. Okay. Now, somebody proved this next thing, and it's really hard to prove. I proved it once in my class, and it took about a half an hour to prove it, and it confused a lot of the students because it was so complicated, so I'm not going to do that for you. But it would be done in a real analysis class in college. What they proved was, everywhere the power series, and I'm going to go this to step 3, the power series diverges everywhere else. Where you found it converged, absolutely, it ends up diverging every place else except possibly at the endpoints of the interval that you found in part A. So that means in step 2, you have to check the endpoints, which means you're going to have the 2 endpoints. Those are values of x that you're going to have to plug into the power series, and then you get just a regular series, and we can use all the tests we've used before. So anyway, that's the test for convergence. Okay, so let's just do 3 examples, and then we'll call it a day. So this should look like a power series to you. This is your c sub n, and this is your x minus a to the n. If I want to know where it converges, what I do is I take rho, I'm using the ratio test to be the limit as n approaches infinity, but we're doing it on the absolute value of these terms. So since I'm doing the absolute value, I can ignore the -1 to the n. And I just get what? X minus 2 to the n plus 1 over 2 to the n plus 1. I'm taking the n plus first term and dividing it by the nth term, because that's what the ratio test does. Well, when you divide it by this nth term, it's like multiplying by 2 to the n over x minus 2 to the n. So that's what rho is. Now, can I simplify that? Well, x minus 2 to the n plus 1 over x minus 2 to the n is just x minus 2. But it's still in the absolute value, and 2 to the n over 2 to the n plus 1 is just 2. And the ratio test converges whenever rho is less than 1. So this time, instead of getting yes, it converges or no, it doesn't converge, this time we're going to get where it converges for what values of x. So I get x minus 2 is less than 2, which we already solved to be 0 to 4. So, as some of you probably noticed, this series that we decided to test with this new test is the same as the second power series I did earlier. It's that geometric series. And where did we find it converged by knowing that it was a geometric series? The same thing as this test showed us. So I was just trying to give you the same example to give some confidence into this test. And let's do this. The last power series that we did, the one that seemed to look a lot like e to the x. Well, let's do it on this, because we don't have anything to compare it to, but we'd like to know where it converged. So we would say rho is the limit as n approaches infinity. And you always do absolute value, so it'd just be x to the n plus 1 over n plus 1 factorial divided by the nth term, or multiplied by the reciprocal of the nth term. And again, you can usually simplify these things. You get x to the n plus 1 over x to the n is just x. And n factorial over n plus 1 factorial, remember, n plus 1 factorial is just n plus 1 times n factorial. So they cancel and you're just left with n plus 1. And you still have what? The limit I didn't think I did it over here. I took the limit away because there's nothing left. The only thing left is 1. So that just goes away. So rho just turns out to be the absolute value of x over n plus, well, I'm sorry, this time the limit does really matter, because on this one, there is no more n's left. So you just have this right here times the limit as n approaches infinity of 1. On this one, we have this absolute value of x, and then we still, since the limit does have to do with n, I still have 1 over n plus 1. I can't take that outside of the limit, and I don't really want to. So where does this rho turn out to be less than 1? Well, what about this limit? It's going to 0. So even if I picked 1 billion for x, 1 billion divided by n plus 1 as n approaches infinity is going to go to 0. So that means for all values of x, this is going to be less than 1. So it converges for all real numbers. So this is a really powerful power series if we could find out the function that it converges to. Now, I think it must have been a coincidence, but wouldn't that be really cool if that converged to e to the x? Then we would have a polynomial that we could represent e to the x by. That would be so neat. Okay, let's try one more that's different than a power series we haven't done yet today. So we have 1 over n plus 1 squared is our c sub n, and 1 is our a. So rho equals the limit as n approaches infinity, and we have the absolute value. You get x minus 1 to the n plus 1 over n plus 1 plus 1 squared. So n plus 2 squared divided by this nth term, or multiplied by the reciprocal. Now, what can I take outside? X minus 1 to the n plus 1 over x minus 1 to the n is just x minus 1 to the first, but it's still in absolute value. Now, inside the limit, we have to leave everything that has to do with n. So we get, in the numerator, n squared plus lower powers of n. In the denominator, we get n squared plus different lower powers of n. But as n approaches infinity, this is all going to just be 1. So what do we see? The center is 1 and the radius is 1, so this is going to converge on the open interval from 0 to 2. That's step 1. So what do we have to do? We know it diverges everywhere outside of from 0 to 2, but we still have to check the endpoints. So at x equals 0, what do? We just take the original series and put 0, and the other one we're going to want to put is 2. I'm going to put in 2 first. If I put in 2, what do I get for my series? 2 minus 1 to the n, which is just 1. So the series just becomes 1 over n plus 1 squared. Well, I can compare this to the to the p series 1 over n squared. This converges, and these terms are even smaller. So I know that this one converges. So it does work at 2. So I can put that in. Now, what happens if I put in 0? If I put in 0, I get negative 1 to the n over n plus 1 squared. This one is an alternating series. And I can see the limit as n approaches infinity of 1 over n plus 1 squared does go to 0. And the terms keep getting smaller. So by the alternating series test, that one also converges. So at 0 and 2, the two endpoints, we've now done step 2, and we know it diverges everywhere else. So this particular power series, again, we don't know if it converges to some function or how to find it yet, but if we find it, we know it's not quite as good as this one. Now, as I was doing this, I remembered we did forget on this one to check the endpoints. We found out it went from 0 to 4. So we know it diverges everywhere else. Let's try at 0. And let's try at 4. I'm going to try at 4 first. What does this series become when x equals 4? Well, 4 minus 2 is 2 to the n over 2 to the n. They cancel out, and you just get negative 1 to the n power. So you get negative 1 plus 1, negative 1 plus 1. The terms themselves do not go to 0. So by the alternating series test, this one diverges. Now let's try x equals 0. If I get 0 in here, then I have, I'll rewrite it. You get negative 1 to the n times negative 2 to the n all over 2 to the n. Well, you can write negative 2 to the n as negative 1 to the n times 2 to the n. And the 2 to the n's cancel. Oops, that's an n. So you get negative 1 to the n times negative 1 to the n, which is negative 1 to the 2n. Well, that's just always an even power, so you're just adding up 1's. And that certainly 1 plus 1 plus 1 forever is not going to converge. So both of the endpoints diverge. So that is the answer. But we really did have to check the endpoints. So anyway, that's pretty much what a power series is. Don't be afraid of power series. They're just polynomials. What's going to be important is finding out where they converge, and then maybe we've only found 2 functions in this one that we don't think really is, but we would like to be able to find more functions that we can represent by polynomials. So I will do, the next lecture will be a continuation about power series, and we'll see if we can find some more functions. So, take care.